Hello everyone, my name is Edlin Garcia and this is my submission for Lab 3 Digital Signatures in Python. I've created two separate Python programs to demonstrate how a message can be signed using RSA and then verified securely by another client. These programs simulate the core process behind digital signatures, ensuring both authenticity and integrity of a message. I did not see any specific tools listed for this lab, and I was not really familiar with Python, so I used Visual Code for my code editor and Python 3.13 version for the language. So, the library used in this lab was RSA, which is a Python library for RSA key generation, signing, and verification. I also worked with basic file input and output and used that PEM format and rely on SHA-256 hashing. So I'm first going to open my folder with the files. Okay, so before I did not put to trust the authors and it had an issue with importing Python. So to avoid this issue, ensure that you select yes, I trust the author or not, it's going to block some of the features of the Python extension. So here I have my file for client A and then client B. So let me walk you through client A, which is the signing side, as if though I'm Amy, the sender. So I started by generating a public-private key pair by using the RSA.new keys 2048 which should be the minimum allowed in RSA. Then the message is stored as bytes since the signature algorithm only works in binary. That's why we have the B in front of the message written. Hello, this is Amy. Welcome to Belize. So here is an alternative way of how the message could be sent to ensure that it was encoded in bytes. You have message equal, you type your text and you put that encode in brackets UTF-8. It would be encoded in UTF-8 instead of just using B. Either way works in this case. So finally, I would sign the message using Amy's private key and SHA-256 algorithm. Then I just entered a print message sign to ensure that or confirm that the signature has worked. Then finally, I actually write the message to the message.text. I write the signature to signature.text. These will be files that are created and written to. And I save the public key.pem for Amy. So this one is optional, but I also save the private key for future use if you'd like to use the same key for future testing or expansion. Let me open client B before I actually run it. So for the second program, client B, this is the verifying side. So now I will run through it like I am client B. So in this case, I load the message, signature, and public key that was generated and saved to client A. Then by using RSA verify function, I verify the signature and ensures that it matches the message. If it's valid, it will output signature verified message is authenticated. If it's not valid, then it's going to output signature verification fail message was tampered with. In my code here, you'll see that there was an alternative way to write the code, but I chose to use the source code that was given to us. This is the source code that was given to us. I use this to structure my code. You can write it either way or follow another source code and also other tutorials to help me understand that the try except was the best way to handle this case because it avoids the program from crashing. If it fails, it will just clean it up and return this message signature verification fail. The alternative way without the try except that handle errors would be just to put the RSA verify message signature public key and print that it was verified. Again, either way could have worked. I chose to put this way to handle any error in case, right? So some challenges I faced, like I mentioned, was being unaware that my environment was restricted. So an alternative way could have been to go to manage or click the restricted option and change to trust environment, and that would allow you to import RSA and run the program. You could also ensure that Python is installed by going to the terminal and type py-m pip install RSA, and then it would show that the requirement was already satisfied. So let me run client A to show that it's working. Okay, see we have the output here, message sign, and if you check in our folder here, we have the message text created, the private key.pem, public key, all being saved along with our signature key. If I go to client B and I run client B now, we can see signature verified, message is authenticated. So now we have confirmed that our digital signature works. So if I open message at text, we have hello, this is Amy, welcome to Belize. The message has been written. The signature text cannot be displayed here because it's in binary. Let's see if I can get it to display here. Again, see, it's in binary. We can't understand it, but I just wanted to show that the files were actually created and we got our confirmation messages here and the items in our folder. So, in summary, this lab taught me how digital signature works in practice. I used the private key to sign and the public keys to verify. This ensures authenticity by the sender, ensures that the sender identity is actually, Amy in this case, and the integrity wasn't altered, meaning that the message wasn't altered. So I was able to verify those two through this lab. And most importantly, I also learned how to troubleshoot my tools in this case, especially how VS Code, the Python environment, and extension interact when building a security based application. So, thank you for watching my demo and walkthrough.